Good.
Maybe Josh is going to start, but maybe just in terms of introductions, right? My name's Todd Rossi. I'm from Rutgers University. I did my PhD here at Purdue. Professor Braun was my PhD advisor back in the 1990s. I did my PhD in fault detection diagnostics of packaged HVAC equipment, right? And Josh is a master's student at Rutgers, and he and I have been working on unit coordination that Duncan was just talking about. So go ahead, Josh.
Yeah. In the spirit of the Intelligent Building Operations Workshop, we focused on implementation and commercialization of this technology, since there's been a breadth of research over the last 20 years or so on it. Dr. Rossi introduced me to the topic of rooftop unit coordination a few years ago, and we started by trying to use a Ecobee thermostat to control a quick serve restaurant with 3 zones. And the objective was to use the multiple unitary electric cooling loads to distribute them by anticipating what the cooling loads will be ahead of time. And by cooperatively controlling the building using a supervisory control algorithm, reduce the overall demand of the building. You can have rules-based unit coordination, or you can have a model predictive unit coordination. The application we chose was to take the model predictive route. This is just an outline of what we're going to go over. So there's 2 benefits, or there's 2 audiences which benefit from it. There's the client, which benefits from having the reduced costs from their demand being reduced. And in addition to that, when a unit is performing poorly, there's a kind of built-in mechanism when you use model predictive control where a unit that is more effective at delivering the cooling load will compensate and will be prioritized in the algorithm and deliver cooling. So there's some built-in benefits to the client as far as comfort goes, not just to do with demand. The control algorithm that we implemented does do pre-cooling in order to try to bring down the temperature of the building, not in response to price signals, but just in anticipation of dramatic set point changes. So you can imagine a situation like Dong-Hoon brought up, where the building will transition from unoccupied to occupied, and all of the units will ramp up at the same time. And so in addition to the model predictive control, we implemented a regime at the very beginning when the building goes into its operating period, where it walks down the temperature set point. The other beneficiary of unit coordination is just the overall grid. The less peaky the grid is, the more easy it is to operate, and the grid needs to deliver power production to the peak. It's not so. If you can lower the peak by even a small margin, then the overall amount of electricity that needs to be generated in order to accommodate for those peak events also goes down. This is just representing a 1% decrease in the power generation in the United States, which is around 44,000 gigawatt hours, or 51 million barrels of oil, 20 million metric tons of coal. In order to size the opportunity, there are certain steps that you can take in order to make a case for why model predictive control or unit coordination might be beneficial to a client. Dr. Rossi was going to go over some of the ways that you can try to size the opportunity.
Thanks, Josh. So this is an example of identifying the opportunity that specific clients have. So Josh is going to explain a project that we're doing with NREL right now about this, but this is the other partner with us in NREL is Cinemark Movie Theaters. They've got like 250 cinemas around the country, approximately like 40 rooftop units in each one. And so one of the, just stay on the other slide, Josh. So one of the things that, out of all the benefits Josh mentioned, we're focused on the demand savings one in this particular case. And one of the things that we did was looked at, out of all of their sites, which one had really high demand charges and focused on those. So this one in El Paso, Texas, 236 is one, and then there's another one in California somewhere, right? It doesn't matter. There's another one that we identified, so we're doing the pilots in those two. And one of the things that was investigated here was, as Jim pointed out a long time ago, one of the opportunities to deploy this from a commercially attractive perspective is if it's only have to interface through the thermostat, right? So the first column, the HVAC savings, is if you just take all the thermostat data and convert the run times into an estimate of kilowatts of power, right? And you looked at how much savings you could get. And you could see this is 3 months of a year. So there's an EMS system that has all the HVAC and run times and so on, as well as a power meter for the building, right? Every 15 minutes. So you can see in these 2 particular months, there's significant savings associated with applying, being able to smooth out the peaks in those 2 months. And then what we did was we looked at, the reference point for smoothing out, this has nothing to do with deploying a solution, this is just a reference point. And one of the reference point tools that we use is just apply a low pass filter with a time constant of 1 hour. So it says if you were just able to take that peak and smooth it out, are there essentially peaks that could be smoothed out, right? This is the savings that you get from it. You can see the average savings down below is like 16% of it's a percentage of the HVAC energy use, not the percentage of the total. So on average, but you can see it varies a lot each month. And then the meter savings says apply the low pass filter to the whole building energy use, not just the HVAC energy use. And you can see you get about the same percentage of savings. But the other interesting point that I was trying to make with this is, what happens, how coincident is the HVAC peaks with the building peaks? Because if you're not looking at the building total energy use and you're just deploying with the thermostats, which is really attractive commercially, like we always sort of made an initial assumption that the HVAC peaks align well with the building peaks. And it turns out that you can see that it varies a lot. And I highlighted 2 examples. 1 month where you got most of the savings and another month where the savings was completely non-coincident, right? So what I'm going to do in the next 6 slides is explore those 6 different examples in there. So go to the next one. So this is March where it worked. And you can see when you look at the peak for the HVAC and then you look at the low pass filter HVAC, you can see how it went down substantially, right? So it worked. 74 kilowatts of peak demand savings of just HVAC. Next one. This is the whole building meter. And you can see this one peak on the left one is with the meter, and then the low pass filter is in red, and it's down below there. So that's the shift of the peak. And it worked there too. You got substantial savings. Now go to the next one. So in this case, you can compare the peak of the meter with the peak of essentially what this is what we did is we took the whole building, subtracted off the HVAC, and then replaced the HVAC with the low pass filter, right? So that's the benchmark. So you can see in this case, it worked. You got 60 kilowatts of savings combined if you just did the thermostats and ignored the whole building meter. Go to the next one. So this is May, a month where it didn't work, right? So you can see there's this big HVAC peak early morning on the one day. That set the peak for the month. And then the next few days later, with the low pass filter, after you eliminated that peak, the peak shifted to this other place a few days later. Next one. So there's the non-HVAC peak over there, but you can see with the whole building meter, there was still 24 kilowatt hours of savings. It looks like it's in the noise, but this building has 400 or 500 kilowatts of peak, right? So you still generated that, but go to the next slide. So this is one where it didn't work, right? Where you could see that the HVAC peak that was eliminated all the way down there on the left side, it didn't contribute to the whole building peak at all, which was over on the other day. And so eliminating that peak that the thermostat saw didn't result in that month in affecting the overall thing. So now I'll hand it back to Josh.
Yeah. So that curve smoothing out the HVAC load method is a way to kind of estimate what the load flexibility, how the load flexibility could be leveraged in the building in order to distribute the loads. The control algorithm that we used makes an assumption that the demand is being assessed on fixed 15-minute intervals, so they're discrete intervals. And the way that it works is that it looks an hour ahead, and it runs every possible runtime sequence for each of the zones and each of the units. So it'll run on off for however many units there are, going forward an hour. And then it'll identify the minimum peak occurring in any 15-minute interval. One of the problems with this approach is that because it's an exhaustive search method, you run into problems with combinatorics when you try to scale it, because as you introduce, when you have 2 units, there's only 4 possible runtime sequences. When you have 6, it goes up to 36, and it just keeps on going. So another point to make here is that every 15 minutes, it will re-optimize and assess a new minimum peak demand, and that's acting as a limiter, and the units won't be allowed to run above that kilowatt threshold. And so in order to allow cooling loads into other zones, aside from the ones that were originally assigned at the initial 15-minute optimization, it will shuffle at the 5-minute marks. So we'll shuffle the units in order of priority in order to deliver cooling loads to the other zones in the building. It was important to make a distinction between the unit coordination server and the thermostat interface, because the interface is going to change. You're going to have a JACE, or you're going to have an Ecobee thermostat, or some sort of smart thermostat. And so you need to design a control layer that is agnostic to the unit coordination algorithm. The unit coordination algorithm just should receive the variables that are needed to run the optimization, and it should not care at all what it's interfacing with on the other side. So there should be an interpreter layer. This just goes into the same thing. So you're going to run into a bunch of different kinds of interfaces, and you need to have a go-between that collects the state variables from the proprietary systems and spits it out in some pre-formatted way in order for the unit coordination algorithm to be able to run the optimization. The server that we uses an Apache HTTP receiver, which basically is like an API that anybody can set up for themselves. This is an example of in the quick serve restaurant where the controller avoided setting a large peak. The orange line is the percent RT full load, and this is when it's transitioning from unoccupied to occupied. So rather than allowing the units to all snap on at the same time, it lowers the set point temperature gradually in order to ease into the occupied period of the day. The algorithm that we used for the initial test with the quick serve restaurant is going through a validation process with NREL right now. They're trying to validate the software with a Energy Plus model, and they're using the Cinemark building that Dr. Rossi referenced earlier. The reason they're able to use the Energy Plus model is because they have a wrapper that goes around Energy Plus called Alfalfa that allows you to step forward. Usually when you run an Energy Plus model, you get kind of aggregate data that spits out all at once. And you might have the time series data, but you're not able to implement any kind of changes along the way. So you only get the final outcome. The Alfalfa model basically allows you to step forward in minute increments. So you can make changes to the set points the way you would with the thermostat. So these are the results from the alfalfa simulation. This ran for the month of May. In blue is the percent runtime for each of the units. And it's identifying in this period of time was the peak event. So in red is the baseline, which is the Energy Plus models without any unit coordination. And in blue is with unit coordination. And this is just the percent runtime for each unit for these intervals. It resulted in a 27.7 kilowatt decrease for the month of May and resulted in $750 of savings. That's why you need to be conscientious of what the opportunity is for these clients, because you have to keep your implementation costs low, as Donghu mentioned, and you have to make sure that this is a realistic strategy for them. Another interesting thing that was beneficial for using the simulation software for testing was that we realized that we'd actually had decreased the amount of uncomfortable degree hours in the building. And so it's likely that our algorithm is perhaps over prioritizing comfort, and we could probably relax that constraint and realize better kilowatt reduction. So some of the lessons that we learned from the practical application was to do with when you're using the smart thermostats to control the rooftop units, there's often a delay, and the delay affects how you model the thermal zones, because you may need to offset the changes in the building temperature by one time step in order to actually have an accurate model of the cooling load's influence on the thermal zone. And when you actuate the units using the temperature set points, you kind of lose the nuance of staging, because it's difficult to know exactly how the internal control of the rooftop unit is responding to these deadbands. And so if you look closely, you might be able to say, okay, at 1.2 degrees, it will initiate stage 1 cooling, but it's not a reliable thing. So usually you have to kind of overshoot it, and then it becomes a single stage unit in effect when you do it that way. Simulation testing turned out to be good for us because there was quick turnaround of results. We were able to iterate on the algorithm and improve it, which was needed because we went from a 3-zone test case to now working with Cinemark, which is 29 different zones. So we needed to make some significant runtime improvements, which involved parallel processing of the sequences. Oh, and it's also good for benchmarking, because when you run the simulation software with and without, you don't have any of the variability in the climate, because you're just running the same TMY data on the ambient.
Okay, so I'll finish up here at the last 2 slides. So just to pick up on the NREL exercise, it's not just a technical exercise to demonstrate how it performed. It's specifically to help sell the algorithm, so it speaks to commercialization. So the reason why we partnered with Cinemark, and they specifically calibrated the Energy Plus model they made to the Cinemark theaters, is that the idea is to try to help a client like that adopt the new technology like this by modeling their building and showing them before they invest and take risks in implementation on what the benefits could specifically be for them, is part of the goal of the objective of it. To speak to sort of commercialization more broadly, I think the first point that I want to make is understanding the opportunity. The story that I told about the peak demand reduction has nothing to do with the deployment or the solution. It's just seeing what the opportunity is that's out there. And so there's other benefits other than peak demand reduction. But my sense is that if you're kind of thinking about the commercialization opportunity, to understand fundamentally what the opportunity is before you get to solving it is a helpful first step. The second one is to demonstrate the solution. In other words, make a solution like we did, deploy it and demonstrate it. I sort of feel that it's best to do it before you even start worrying about making money with it, right? It's just get it out there and demonstrate that it works and get people's feedback about whether they care or not, right? And that was a hard lesson learned from previous things. And if you do that, one of the things that I've kind of learned was that before you start asking anybody for money in step 3 is after you've deployed it and got their feedback, you have a better sense of the context of the solution and the other side benefits of it, and they can give you better feedback about how they benefit from it, because you build a model of something, as Gregor says a lot of times, right? You can use the model for lots of different things, right? And if you're comparing to models, you can have references for fault detection, and that speaks to things like maybe never charge for unit coordination. Maybe it gets stuck into a service contract for an HVAC unit, right? That maybe is really big compared to the cost of this, and then they get all the other side benefits. So my point is don't worry about making money with it initially. Just actually go out and do it and show that you can do it and that people care about it. And the money thing, I think, will become clearer later. Last slide, Josh. So in conclusion, we think we've demonstrated some insights into the opportunity. Josh explained how we created a control solution for it around MPC that's kind of built on the work Professor Braun and Dong Hoon did and so on. We're working with NREL to demonstrate this solution. We have a particular commercialization approach. So in the spirit of the commercialization approach, we continue to work with NREL to expand to some more cases that we need to understand more clearly, building on what Josh reported. We have a deployment with smart thermostats now that we're doing with some quick serve restaurants, and we want to expand that. We also, as well as Cinemark, actually doing it with them. And then finally, like I just said, we really want to get to the point where we get these clients understanding what we've done for them and try to understand from them how much they care and how they would like to do it. So for example, we spoke to the quick serve guy a couple weeks ago, right? And James said to us, he started already thinking about shared savings like model, right? And so it's good to kind of see like naturally how clients are thinking. He was worried that if we use the baseline of this year and we did unit coordination, what happens when he makes other changes, right? And the baseline changes. He's already sort of thinking about that. So we want to have those kind of conversations as we sort of prove out the solution and get more experience before we start thinking about making money with it. Thank you very much. Okay, got it.
Okay, thank you very much, guys, for the talk. It was fascinating as well. I'm going to start with a question from, again, Gregor online. So let me see if I can remember it. Oh, he asks, what is the objective function in the MPC deployment that you did? I think it was in the quick serve. Was it strictly peak demand, or did you have a term in there around comfort or a term around energy cost, for example?
Do you want to answer, or do you want to?
Yeah, it runs every single sequence of possible ways that the units can run over 5 minutes, and then it first prioritizes comfort, and then its second priority is the lowest demand possible over a 15-minute interval. So the first priority is comfort, and then you can add a tolerance to that comfort priority if you need to.
There's no energy.
No energy there. Okay, thank you.
In terms of getting set up with one of your clients, what is the kind of this initial setup cost? How much configuration is required? How much information from the building do you need to have? Can you just elaborate? A big part of commercialization is kind of getting it set up, installed, and configured. Can you elaborate a little bit on that? Sure.
So Professor Braun articulated a vision a long time ago about how you really want to be able to do this with really low cost. That's the whole idea of the thermostat only approach, right? So we're trying really hard to kind of keep to that. And so by using like these, there's Nest or Ecobee or whatever, but by using these internet connected thermostats that are already providing you data and stuff, it creates a great platform for that. So we have that, and obviously we need to know how many tons the unit is, right, in order to estimate kilowatts from that. But we try to keep any other information about the unit really to a minimum. I don't think there is anything else other than an estimate of the nominal capacity. And we try to like keep it down. And then my spirit of commercialization, other than having that overall philosophy and trying to head in the right direction that way, I think we're avoiding really trying to worry about the monetization till later to see how the details all come together.
If they have smart thermostat, then the historical data that's stored by the smart thermostat provides a lot of what's required to do the modeling. So that's a big benefit.
I also think like the connection to the whole power meter that I was saying about whether you need to know what the whole building is doing to really understand what the real peak is an interesting question. So we're kind of wondering whether we really want to invest in solving that problem as part of the solution or just go after it just with the thermostats.
Just to follow up on that quickly, so how did you connect with your two kind of early adopter clients, QuickServe and Cinemark?
Well, they were, sort of built the business for a couple decades, right? So we just the short answer is that we've just been out there selling really hard to try to find those early adopters, and they're just one of many people that we stumbled into. They're just, it's just a lot of hard work. Yeah.
And are they paying you guys at all, or are you kind of doing stuff for free
money.
for now?
Don't ask for money. Yep. I think the whole idea is let's show that we can do something first, and then we can figure out the money part later. I mean, the conversation comes up because people know they have to pay for things. But I had this conversation with a customer recently on a different project. He eventually said, I know you're giving it to us for free, but we know that you have to pay for things. And we're getting nervous because we're starting to count on it. And we know that we can't count on it if we're not paying for it, right? And as soon as that happens, you're in the golden spot, right? Where they're essentially like selling for you, right? And that's...
I love that approach. I think we had a question from the room here.
Just very quick, generally, do you think the approach of thermostat preset or pre-cool will extend the benefits in the world of variable speed systems?
Yes.
Okay.
Simple answer.
Is there time for one more question?
There's a question. Is there a strategy of communicating to them the potential performance gaps of such technology over multiple years?
You want to answer that, or?
Could you rephrase the question?
Is there a strategy of communicating to them the potential performance gaps of such technology over multiple years?
I think that we would offer the technology for a year, just as a demonstration, and that if the effects are significant, they should speak for themselves. If it's hard to make the case that they've realized some savings, then you might need to go back to the drawing board. So I think that once you demonstrate the value, that it will be a no-brainer for a business owner to pay for it, either by shared savings or subscription model.
Yeah, I'd just add to that a little bit. I'd say go back to the same point I was making. Don't worry about money, right? But in terms of looking multiple years ahead, there is a distinction between when you're modeling using the actual weather data for the year that you may be comparing to the utility bill versus TMY data. So I think if you want to anticipate what the benefits are going to be over a typical year long into the future, then you use TMY data for that. So maybe that helps.
Okay, I have one more. I really like the model of having NREL basically do independent validation. So then if there are demonstrated benefits, it's not coming from the company necessarily who has a financial interest in selling something. It's coming from a neutral third party. So I wonder if you could talk a little bit about that relationship. Did you approach NREL about that? Did the client approach NREL? Did NREL come to you? And then how has the client, Cinemark, how has it influenced that relationship, I guess?
Well, To answer your question, I don't remember how it got started. I don't know. I think it's just part of the network of people that have been collaborating a lot for a long time. And as far as the Cinemark relationship is concerned, I think they're kind of, I mean, don't get the impression that they're waiting at the edge of their seats for this, right? I mean, they're essentially, we've been a trusted partner of them for a long time. We've extracted data from their EMS systems, helped them with projects. And so they're giving us an opportunity to prove that we could make some benefits. And as soon as we go and tell them a story, they're open-minded to a potential reasonable business thing, right? And I'm not too concerned about the details of how the business thing will work out yet.
Okay, very good. Any more questions from the room?
Thank you for a great presentation. One technical question. So you mentioned the cinema has a 40 or 50 RTUs, and as a single stage, two stage.
Yeah, typically each cinema is a zone that is isolated from the other cinemas, right? Within there, that's the model that they told us to use, and that we've been using. In some of the, so it's like I think this one has 29. Like cinemas in it?
It has 34, but
34.
we could only make accurate thermal models of 29 of the zones. So we're coordinating 29 of 34 zones.
Okay. And yeah, there's some challenges with learning the models on some of the zones. And then some of the zones have even 2 units in it, like 2 smaller ones. But they're just standard package units. Yeah. 10, probably at least 10 tons up to 20 in that range, like Walmart would have and so on. Yeah.
So to solve that kind of large systems, then maybe, as you probably mentioned it in the middle of your presentation, the numerical issues to get this optimization solution within the sampling time is gonna be challenging. So do you have any strategies in your mind at this moment?
There's 2 that I could think of. One of them is grouping the units and only trying to coordinate them in sensible groupings. And the other one would just be to, right now the sequences are all run sequentially, and all of the sequences actually could be ran in parallel. So you could concatenate all of the different runtime sequences together if you had a parallel processing procedure. So that's what I was working on now.
Yeah, I think to give you a specific one of that, when we started out with, say, 2 units that are 2 stages, right? Then you have, let's just say it's 5 kilowatts per stage, right? Mm-hmm. Then you can get all the different combinations. Like if you turn this only one on, you get 5 kilowatts. You turn 2 on, you get 10, right? So you can get all those different, those are the decisions you can make. But when the number gets bigger, then those combinations get out of hand, right? So all that we do is we just say that we just pick a number like 10. We're going to set like a peak demand limit of like in chunks of 10 of the peak, right? And you can turn on as many units as you want to until you get to this peak demand limit, right? And we're going to optimize around that limit and then shuffle the particular units around without the optimization problem to that limit. And that was a way of getting rid of that combinatorial problem. But Josh was saying about the exhaustive search method that we use. So there's a bunch of different algorithms that I think we could definitely improve on. But I think what we're trying to do is just for now to keep it simple and keep it reliable so that what we really want to do is see if we can really have an impact that somebody cares about. And then we can then roll some of those resources that will come in as it matures into those kinds of improvements.
All right. Is there one more? Oh, okay, just saying hi. Great. So thank you very much for that. I think we're going to proceed to a coffee break now. Coffee is upstairs where we had breakfast. Let's try to come back into the room maybe around 10 after, and then for folks online, we'll restart the talks about quarter after.
Okay, thank you.